All right, we're going to go ahead and give this old AP problem a try. This actually isn't a problem from an old AP exam, but it is a problem put out by College Board as a practice problem. And it's actually a really nice problem for looking at rotation, specifically rolling motion. In the process of doing this, we're going to talk about angular momentum, energy, force, and torque. So rotational kinematics too, actually. We're actually going to hit every rotational part in the process of talking through this problem. So it really is a really nice problem. So talking through, I'm going to use this. I'm going to do my work on a separate sheet of paper. Here we go. So it says that a cylinder of mass m and radius r is released from rest at the top of an inclined plane as shown above. The cylinder rolls without slipping down the incline. The rotational inertia of the cylinder is 1/2 mr squared. So you say, first of all, rolling without slipping, you say, aha, that tells me things. In order to go without slipping, there has to be friction on it to make it start to spin, right? So that it rolls smoothly. So I know it's not a frictionless incline. But more importantly, it tells me that I have the no slip condition. And so that no slip condition tells me that as it goes, if I look at how fast the center of mass is moving along, that's going to be equal to the radius of the cylinder times that omega, that angular velocity. And again, and that comes from the idea that however, and again, I can also say that my displacement of the center of mass is going to be equal to r delta theta. And I can say that my acceleration of the center of mass is going to be equal to r alpha. And again, this idea here is, starting at the top here, that displacement of the center of mass, how far the center of mass goes, is the same as like the distance a point on the rim would go around, right? And we know that that arc length, or that length that that distance on the rim goes around, that's going to be equal to the length we go along the surface here, right? Because we're not skidding. If we were sliding, right, maybe this is spinning really fast, and it would go around further than it would actually move sideways if it was slipping as it went. Or maybe it's spinning too slowly and it's skidding down and it's moving farther along than a point on the rim would spin around. And so you wouldn't be able to say that how far the center of mass goes is how far a point on the rim would go. But with this case, we can. This is the no slip condition. Okay, and that's going to let us use this. Okay, and that's an important thing to recognize. That rotational inertia being 1/2 mr squared, again, that's a formula. They will tell you generally the moment of inertia formulas for different shapes, unless the whole point is for you to derive it yourself in the problem. I've seen them make you do that before for rods, right? Okay, do that, be able to find the moment of inertia for a rod, and that's where we like split it up into little bits and use that linear mass density to solve. And I've seen, and then combinations of point particles and these. So you should be able to find moment inertia for point particles using the sum of the mr squareds, and then derive for a rod for rotating around various points. And then obviously, if they give you the inertia for different parts, for different shapes that go together to make a compound body, you should be able to add them all up, which we'll do later on in this problem. But yeah, the one that I've never seen them make you derive any other shape from scratch other than rods. Okay, good enough. Moving on. Like I said, they usually give it to you in the formula. Okay, let's move on. First part, derive, and again, this problem's got like 5 parts, A through E, and I think part D has got like 2 or 3 subparts to it. So here we go. Part A, derive an expression for the angular momentum of the cylinder around its center of mass when it's rolled a vertical distance h. And again, like that moment, the angular momentum you get, it does depend on where your axis of rotation is. It's like your frame of reference. So they're saying for rotating around the middle, which is handy because we know I for going around the middle. When it's rolled a vertical distance h, express your answer in terms of mr, h, and physical constants appropriate. There's probably multiple ways of doing this. I'm going to solve this one using energy. I think that's the most straightforward way of doing it. So I'm going to set up. You say, when I go to do an energy problem, I'm sorry, we're trying to find angular momentum, right? So I'm jumping ahead. And I say, hey, what formula for angular momentum am I going to use? And you would say, well, I omega. My other formula, L is R cross P. That's more for if I've got a point particle moving with some momentum P. So I'm going to use this one for shapes, like the cylinder. Okay, now the nice thing is you say, hey, I, that's going to be easy. I know that I is 1/2 mr squared. Okay, they gave it to me right there. But you say, but wait, I don't know what that omega is yet. Okay, and I'm not allowed to have an omega in my answer. I've got to have just m, r, h, and physical constants. By physical constants, they mean like universal constants, or or little g is a constant near the surface of the Earth. So like little g, or like universal gravitational constant, big G, or later on we're going to talk about like the mass of a proton or the charge of a proton or an elementary charge. Those are constants that we can use. Okay, anyway, in this one we're going to be using little g. I don't think that's a shocker to anyone. Moving on. So like I said, so I need to find omega. I think it makes the most sense to do this with energy. Are there other ways of solving it? Probably, but we're going to use energy for this one. So when you do an energy problem, you always have like a starting point and an ending point. We're going to go ahead and use, let me switch colors here. Sure. We're going to go ahead and do a sum of the works is equal to delta K, right? And you say, well, I got to choose a system, and you say, certainly the cylinder is going to be my system. I'm going to go from when it starts till it's gone down a distance h. So we're going to go from here to here. You say, what outside forces are going to act on the cylinder? And you're like, well, there's going to be gravity and a normal force from the ramp and a frictional force with the ramp, because it is rolling without slipping. There's got to be a friction force to tug on it and make it rotate. You say, well, if I run through those, will they be doing work? And you say, well, the normal force is perpendicular to the motion. It's not going to do any work. And the friction force is a static friction. I'm rolling without slipping. That means each part just comes in and out of contact with the surface. We're not like skidding along. The friction isn't acting through a distance, that static friction. And so it doesn't do any work. So the only force left to do work is the gravitational force. I'd rather not calculate a work by gravity if I don't have to. I'm going to expand my system and include the Earth. And so that means, because I'm including the Earth, that means I can have a plus delta UG here. And I've now made sure that all three forces acting aren't going to do work. So I got no work terms left. Now the trick here is to remember that there's actually two kinds of delta K going on. I've got a kinetic energy because I'm translating along the surface, a 1/2 mv squared, and I have a rotational kinetic energy because this is spinning while it translates. So I'm going to have two delta Ks, a delta K rotational and a delta K translational as I go down the ramp. Okay, let's expand out our deltas and see if any of the terms are going to drop out. So I'm going to have a K rotational final minus a K rotational initial plus a K translational final minus a K translational initial plus a UG final minus a UG initial. And so you say, hey, which of these are going to be 0? And you say, well, I know that I start from rest, right? Release from rest. So all the initial kinetic energies are going to go away. Bam, bam. And with potential energy, with gravitational potential energy, I've got to choose somewhere to call height 0. We're going to call it the bottom here, height 0, and we're going to start at a height h. So at the end, we're ending at height 0, so we'll have no potential energy, gravitational potential energy at the end, so that term goes away. So now I just have 3 terms to deal with instead of 6, and that makes me feel much better. Let's go ahead, I'm just going to expand those out as we go. So my K rotational, that's going to be a 1/2 I omega squared. And then my K translational will be a 1/2 mv squared. And then my UG initial is going to be a mgh. You notice I'm putting in capital M's, that's their variable for the mass of this object. I'm going to right away put in using their variables. So here we go, I have an equation, it's got an omega in it, I just need to get an omega in there to solve. And you say, well, I can see it's got an I, and I'm not allowed to have I in my answer. That's easy, I've got the formula for I, 1/2 mr squared, and that'll be okay. The V I'm not allowed to have, so I need to rewrite V. but everything else here is okay. So it's just the I and the V I got to get rid of. And you say, well, the I is easy. It's 1/2 mv squared. And this V, though, you say, well, I'm going to get rid of that using that no slip condition. This velocity is the velocity of the whole thing moving down, like translating down. Well, that's the velocity of the center of mass moving down the hill. So I can put in an r omega where I see V there, right? And you say, well, it's a V squared, so it's going to be r squared omega squared. All right. And once I've done that substitution, then you say, well, look, I can simplify this quite a bit. There's a mass in every term. So bam, bam, bam. I can probably, did I really just copy down? I'm sorry, I is 1/2 mr squared. What was I thinking? Sorry. That's better. Okay, sorry. I can see that I've got an m in every term. I'm gonna see there's a half there and a half there. I'm just gonna multiply through by 2 and tidy that up a little bit, if that's okay with you. So every term times 2. So then 2/2 is 1. 2/2 is 1. There we go. Okay, so what have I got now to deal with? Well, that tidied up to be 0 is a 1/2 r squared omega squared. And here I've got another, and I've got a 1 r squared omega squared. And then I've got a minus 2gh. Okay. So here we go. Let's move the 2gh over. 2gh, right? Add it over to the other side. And then let's say, look, I've got a 1/2 r squared times omega squared and an r squared times omega squared. So that's 3/2 r omega squared. R squared omega squared. I'm going to move the 3/2 r squared over here and then take a square root. And so I'm going to get 4/3 gh over r squared. And that's going to be my omega squared. So I'll take a square root. That's the omega I need to plug in there. Let's see here. I can see a square root. I can take a 2 out, and I can take an r on the bottom out. So it'll be like 2 over r times the root of gh over 3, right? That's my omega. Okay, so that can go in there where it says omega, and I'll have my answer. I guess I'm going to go ahead and move that up there. And then where it said omega, we've got a 2 over r root of gh over 3, right? Okay. And I can see this 2 on top and 2 on the bottom, bam, bam. This r will cancel one of those r's, that r squared, right? That square there. And so I'm ending up with an L equal to mr times the root of gh over 3. Okay. Now the problem is, yeah, so that's what I get. Okay, and if I double checked, we could double check that the units come out right and they give you angular momentum units, but it's going to be just fine. Okay, so there we go. So that's our answer for part A. All right. Okay, move on to the next part. Okay, the next part of the problem says, hey, is the angular momentum of the cylinder conserved as the cylinder rolls down that vertical distance h? Yes or no, and justify your answer. And so you say, well, is L conserved as it rolls down? You say, well, look, as it rolls down, here's the equation for L. Is the M changing? You're like, no. Is the R changing as it rolls down? No. Is G changing as it rolls down? No. Is H changing? And you say, well, actually, its height will be changing as it rolls down. And so you're like, well, then L will be changing. So on the one hand, you can say, no, L is not conserved, right? And you can say, because we can see the height will be changing, and the height is in the equation for L. Okay, so that's one thing. Since you just derived that, you can use that. The other thing is you can say, look, if I want to talk about conserving L, if I want to talk about conserving L, you know that the way you change L is you apply a torque through a time. That's how you change angular momentum. This is the big angular momentum formula, right? Just like the momentum one for linear momentum is integral of F dt equals delta P. Integral torque dt is delta L. And you say, look, there'll be a change in L if there's an outside unbalanced torque. And in this case, there is an unbalanced torque. Okay, you say, wait, why is there an unbalanced torque? Well, there's three forces acting on that cylinder as it rolls down: gravity, normal, and friction. And you say, hey, as it tries to rotate around the middle, the normal force passes, it's from the surface, it passes through. It doesn't have it'll have a sine theta, sine of 0 when I go to calculate a cross product for torque is R cross F, right? My R vector goes, so it'd be a torque sine of 180. The R vector goes down to where the force acts, and the force is going opposite. So it'd be sine of 180, which is 0. Gravity exerts no torque because it acts at the axis of rotation, so it has an R of 0. The frictional, though, is going to cause a twist, right? It's pulling along the surface at an R there at a right angle to an R vector to a lever arm. So it's going to cause a torque, and that's the torque that makes it speed up its rate of spin. It's giving it angular momentum and changing the angular momentum as it rolls along. So since they're an unbalanced torque due to friction. So there you go. So either of those would be an explanation as to why L is not conserved. Okay, which takes us to the next part. Okay, part C. So now they're going to get trickier. They say now a child's toy is going to be composed of 3 narrow cylinders attached around a common axis through their middles, as shown above. So the central cylinder has a mass m, radius r. Hey, that's just like the cylinder that we just calculated for up here, mass m, radius r. But now I'm sandwiching it between 2 other cylinders, right? The other cylinders have a mass m, just like the original one, but radius 2r. Okay, so maybe they're made of a slightly less dense material. Well, less dense material. And so they're going to make the sandwich, these like 3 cylinders sandwiched together. They want us to find an expression for the rotational inertia of the toy around its middle. Express your answer in terms of m, r, and physical constants. So now we're going to be spinning this guy around. That's 3 cylinders together. So we're trying to find angular momentum, moment of inertia. And so you say, well, moment of inertia, our formula for it is that it's the sum of all the particles times their distance from the axis squared, right? The idea here is that I'm going to add up the mr squareds for all the parts. Well, the same thing is going to apply when I have big shapes. If I stick a bunch of shapes together and rotate them all, I'm just going to add up the i's for all the individual shapes. Okay, and that's the key idea that they're checking here. And so you say, okay, so I'm just going to add up all my i's. So my I is just going to be the I for each of the 3 cylinders, right? You know what I mean? And so my i's, the shape of a cylinder, 1/2 mr squared is the formula for the moment of inertia for a cylinder. So I'm going to say, so first I'll have 1/2 mr squared. That's the original central disk, right? Central cylinder. Plus, now, what about these outer ones? You say, well, again, they're cylinders, so it's the same general formula, 1/2 mr squared. And they have the same mass, m, the outer cylinders, right? But they have a radius twice as big. So when I do them, it's going to be 1/2 the mass, but now the radius is 2r that I'm going to square. And then I'll do that again for the other outer cylinder. Right? And this is it. So I'm just going to add those up. When I do this, I'm going to square the 2r, that's going to become a 4r squared. So I'm going to half mr squared and a half 4 mr squared and a half 4 mr squared. So you're going to say that's a half mr squared, half of 4 is 2. So it's going to be 4.5 mr squared. You see 4.5, you can write that as 9/2 mr squared. And that is my I for the whole thing. Okay, so that's that part. All right, going to the next page. So now it says we're going to take this toy, that's those 3 cylinders stuck together, right? In my head, I'm imagining rolling an Oreo cookie. But anyway, toy placed on a narrow track that's inclined at an angle theta above the horizontal. Only the central, or maybe like a yo-yo maybe. Only the central cylinder is in contact with the track. The toy rolls without slipping down the track. So again, rolling without slipping means we can use all these good no-slip conditions when we do our solution. What they want to know here is, on the dot below, which represents the toy, draw and label the forces, not components, that act on the toy. The dashed line is parallel to the normal track, to the narrow track. Each force must be represented by a distinct arrow, starting on and pointing away from the dot. And you're like, that's no problem. I can do my force diagram. Range forces, there's a gravitational force going down. Am I going to call this mg? And you say, no, I'm going to call this 3 mg, because the mass of this each cylinder is m, and there's 3 of them stuck together. So it's 3 mg. Again, I'm using their variable, big M, was the mass of just the central cylinder. Contact forces, it comes next. Now that we've done range forces, what's touching the cylinder? Just the track. Are they being pressed together? Yep, so there's a normal force that goes perpendicular from the surface. Are they trying to slide past each other? You say, yeah, it would try to. Static friction is going to keep it from slipping. It's going to make it rotate. I'm going to have that friction force that way. And that's it. There's nothing else touching the toy, so that's my force diagram. All right, and I'm not going to draw any components. They say not components. They want to make it simple for the scorers, and you're going to need to do a diagram with components probably for later parts of the problem, but don't do that here. This is what they're scoring for this part. Make a separate diagram. Okay, now we go to part II. Derive an expression for the linear acceleration of the toy as it rolls down the track. Express your answer in terms of mr theta and physical constants as appropriate. And you say, look, that's a little different than before. When we did that derivation earlier, we could have mrh in physical constants, right? And now we're allowed to have mr theta in physical. So we can't use h, but we can use theta. All right, so it's a little different. So here we go. This is the part where I know of at least 3 ways of solving this problem. So I want to show you all 3 techniques. So the question is, what sequence should I show them in? And of course, I'm going to show you first I'll show you the way that they put in their solution, right? And their solution guide to this, which is the 3rd method that I thought of, actually. I don't know what that says about the way I think about physics problems, but I'm going to show their solution first, and then I'll show you the 2 other ways of doing it, which actually I think are nicer, in my opinion. But sure, yeah, I'll do it that way. Okay, so here we go. So here's the way they thought about it. The way they thought about it was they say we're trying to find the linear acceleration. So the variable we're trying to find is a, right? And so we're saying, hey, okay, trying to find that acceleration. And so one of the first things that you're probably going to think of is F equals ma, right? Okay, and that's what they did. And so they said, well, let's go ahead and do a sigma F is ma then. And we're doing this for the parallel to the axis, right? Parallel to the ramp along the motion. And if I did that, then I would need to split that gravitational force up into components. I'm going to do a separate diagram for myself for that cylinder. I should have drawn that bigger, sorry. That cylinder rolling down this ramp that has an angle theta. And I'm trying to find the acceleration as it goes down. So there's not like a starting point and an ending point here, really. I'm trying to find the acceleration. And that also implies something really important to us, because they're not saying like, what's the acceleration when it's at this spot? That means the acceleration is going to be the same value all the way down. Doesn't that kind of implied by that question? So it's a constant acceleration. You say, oh, wait a minute, constant acceleration. That means I could use kinematics. Anyway, but that's not the way we're going to do it, because that's not their technique. They first just did this. And so you'd say, okay, real quick, my force diagram. There's a gravitational force, that 3 mg. There's a normal force, and there's that friction. Again, I wish I'd drawn this picture bigger. I apologize. You say, which force would I need to split into components? Again, we're going to think about a coordinate axis going along the ramp, along the motion, and then one perpendicular. Here's my parallel and my perpendicular. I'm going to call along the motion downhill positive. So I'm going to split this gravitational force up. Right? Right angles between the components. This angle theta here is the angle of the hill. Theta is there. So this makes this 3 mg cosine theta and makes this 3 mg sine theta. All right. So now if I did my sigma F as ma, I'd have forces downhill minus uphill. So that's going to be 3 mg sine theta minus friction is ma parallel. Okay, and this A parallel is what I'm trying to solve for. I should make that M big M, because that's the mass. Oh, it's 3M, because that's the mass of this thing, is big 3M. 3 big M. Right, sorry, whew, almost messed up there. So that's what this is going to be. Notice I'm substituting using their variables right away. Okay, now what? Well, my answer is for A, could I just move the 3M over and call it a day? And you say, well, the M can stick around, and G is physical constant, and the theta can stick around, but I'm not allowed to have friction, so I got to get rid of friction. So I need another equation that has friction. Because you're like, can I plug in mu n? Yeah, but there's nowhere I'm going to get a mu from, so I can't do mu n. Mu is not the physical constant they're talking about. They're talking about like a... Anyway, and so you say, so, I can't plug in mu n. Where else am I going to get a friction force in an equation? And it's going to come from a torque equation from doing sum of the torques is I alpha. So that's the other equation I'm going to use to solve, is we're going to use sum of the torques is I alpha. And this is where I wish I'd drawn that diagram bigger. Sorry about this. You say because I want to show torques, which means I got to show R vectors, and I made this too small to show the R vectors. Sorry. I'm just going to talk through it and hope you understand what I'm saying. So torques, twists around the middle. We're looking at this as rotating around the center while it translates. And so you say, well, the normal force won't exert a torque because it acts through that axis of rotation. It's the angle between its R vector from the center of rotation, axis of rotation, to the edge where the normal force acts is 180 degrees off from the way normal pushes. And the sine of 180 is 0. So when I do the torque, the R cross F, the RF sine theta, for that force, for normal, I'm going to get 0. You say the gravitational force, it acts at the axis of rotation, at the center of mass, which is right at the point we're rotating around. And you say, well, that means its R value, it's that little lever arm that goes from the axis of rotation to where the force is applied, it's got an R of 0. And so it exerts no torque. There's just a torque from friction. So there's going to be a torque from friction, which is going to be R cross F, right? We're going to use the formula torque is R cross F. So for that friction force, that's going to be R, the radius of the big disk, big R, times F, the friction force, and then times the sine of the angle between them. You say, what's the angle between an R vector from the axis to the point at the there when friction is acting tangent? It's going to be a sine of 90. And the sine of 90 is just 1. And then my I know, is what we figured out before, right? We figured out that the I for this thing was 9/2 mr squared. Well, I know we figured it out before. I don't know where I put that paper where we figured that out. Anyway, we know that I is 9/2 mr squared. Oh, there it is. Right, we did this derivation. So I'm going to put that 9/2 mr squared in here. Okay, And then you say, now this alpha, that's a variable I'm not allowed to have, but I'm trying to find the acceleration of the center of mass down the ramp. And because it's no slip, I can go ahead and use my no slip condition and say that acceleration center mass is r alpha. So I can say if acceleration center mass is r alpha, then alpha is going to be that acceleration of center mass over r. And so that's going to go in there for alpha. There we go. So what I have now, I am trying to solve for the acceleration. The problem here is that I had that friction force. So I'm going to an equation here with two unknowns. I need to have just one, A. Here, I don't know the friction force, but I do know R. It was given. M is given, R is given. I can go ahead, I can cancel one of those R's right now. Bam, bam, that's square, right? And I have A. So I got two unknowns, A and F, so I'm just going to substitute and solve. So let me rearrange this one for F and then substitute it in there where it says F, and I'll have an equation that just has A's. And that's the way I'm going to solve. If I did that, I'm just going to divide through, but in fact, that R is going to cancel that R. So all the R's drop out. So my friction is just going to be equal to 9/2 ma. And so I can go ahead and put that 9/2 ma in there for friction. When I do that, I'm just going to bring this equation down here, right? I'm going to have 3 mg sine theta minus this 9/2 ma equals 3 ma. Okay, I'm going to move the 9/2 ma over with this to group my A terms, right? I'm trying to solve for A. So 4.5 and 3, or just say 9/2 and 6/2 is 15/2. By the way, that m can drop, can't it? Move the 2/15ths over, so that'll be 6/15. Well, actually, the 3 can make that a 5. So I'm going to have 2/5 when I rearrange. 2/5 g sine theta is my acceleration down the ramp. Okay, and you say, hey, g sine theta has no units, so g has the same units as a, so that makes sense, and that works out. Okay, so that is technique 1. Okay, what did we do? We did a sum of the F forces as ma, and we did a sum of the torques as I alpha, because I had that friction force there that I need to get rid of, but friction is causing a torque, and I'm going to use that to get two equations with friction and acceleration. I had to link A and alpha with A is R alpha, which I can do because of the no slip condition. Okay, and that's the setup. All right, so I found my acceleration down the ramp. This is not too unlike an example I did in class. Okay, now we're going to do it another way. You say, we'll do it the other way, actually, that I showed you to do a problem like this in class. This is actually the first way I thought of to do this, and that is, instead of treating this like it is rotating around a center of mass and translating along, this is that kind of strange way of thinking about it, which is to think of it as pivoting on edge, right? And so we said, hey, if I've got my disk rolling along a ramp, we said when I go and I add up my tangential velocities from the spinning with the velocity of the center of mass, you get this point here kind of going double the speed of the center of mass at the top. And a point at center of mass going to speed of the center of mass. And the point at the bottom here, because it's spinning, it has a velocity of center of mass backwards plus the motion of it forwards, and they balance out. So the speed at the point where it contacts there is 0. Well, going from 0 to v of center mass to twice v of center mass, that's exactly what your tangential speeds would be if this was just pivoting on that edge. If it was just kind of pivoting like this, that's that distribution of v's you would have. And so by doing it that way, So this is going to be technique 2, treating it as if it is pivoting on edge. Right? And you say, now, why would I want to do it this way? Why is this the first way that I thought of? Well, when I do my force diagram, that 3mg and that normal force and that friction force, you say if I think of it as if it's pivoting, rotating around its edge, then it's rotating around this point, right? And if it's rotating around edge, the normal force won't exert a torque because its R is 0, and the friction, more importantly, won't exert a torque because its R is 0. And that's great because it gets rid of the friction, the thing I don't know how to calculate. And so the only torque is from gravity. And you're like, oh. And so I can do a sum of the torques is I alpha, and from alpha I can get A because of the no slip condition. And you're like, oh, that's actually going to be a really nice way to solve, I think. So that's the way I thought of doing this problem. So we're going to treat it like it's pivoting on edge. And so I'm going to do my sum of the torques is I alpha. And the only torque is from gravity. So I'm going to do like an R cross F, right? And the R here, an R vector is going to go from the axis of rotation, which is here, up to the point where the force is acting, which is at the center there. So my little R vector goes that way, and mg goes this way. And you're like, oh, well, wait a minute. If the R vector is going this way, let me grab another color. Right, that's my R. And you say, well, it's actually going this way. And the line of action of the force is this way. You say, really, this is officially the theta for the calculation, right, when I do the cross product. So I'm going to do my R cross, and the force is 3mg. That means it's R times 3mg times the sine of the angle between them. But the thing about this angle is supplementary with this little guy there. This little guy there and that add up to 180. This little guy, that's the angle of the hill. That's the official actual theta in the problem, right? This is actually 180 minus theta, right, is what this angle is. But this is the angle for the cross product, is this 180 minus theta. But the thing is, it turns out, if you have an angle, there's my unit circle, and you say, if I have an angle, that's theta. If I had a supplementary angle, that'd be an angle that'd be 180 minus back off theta. Well, that would be symmetric, wouldn't it? It'd be symmetric. And the vertical part here, which is equal to sine theta, would be congruent. So the sine of 180 minus theta is the same as the sine of theta here. And so I can just write that as sine theta, which is easier to think about in my head. Okay, on the other side I got I alpha, all right? Now, this is the part that gets tricky about this, is to remember, they tell you, hey, the moment of inertia for a disk rotating around its middle is 1/2 mr squared, but we're not treating it as pivoting around the middle, we're treating it as pivoting on edge. So I've shifted the axis of rotation from the center to this edge. So I have to use the parallel axis theorem to find my new I. So my new I is going to be the I around the center of mass. Whoa, 3m is my mass. I around my center of mass, 1/2 3m r squared plus md squared, right? That's my parallel axis theorem. It says my I new is equal to my I around the center of mass plus md squared, where d is how far I've shifted the axis. In this case, I shifted the axis from the center of mass, a distance r, so I'm going to add an mr squared. But wait, it's not m, the mass is actually 3m. There we go. So that's my new I. And then alpha, you're saying we're not trying to find alpha, we're trying to find A. But because of the no slip condition, we know that A is R alpha. And so where it says alpha, I can plug in A over R. There we go. So when I do this now, here we go. What have we got? We got 3 mr squared, and then this is what, 3 halves mr squared? So it's like 1.5 plus 3, that's 4.5, which is 9 halves. Sure, I'll just do that for now. Mr squared, A over R. So now I have an equation that has actually just the variables I want and A. Now, you cannot leave it like this. They want you to solve for A. That means you got to get an equation in the form A equals something, right? So I got to get the A by itself. Okay, we can tidy this up. It's not that hard. Hey, this R in the bottom here, you're like, bam, it's going to cancel that square. Hey, there's an R here and an R on each side. Bam, bam. All the R's are gone. There's an M on this side, M on this side. Bam, bam. I'm going to take that 2/9 and bring it over. That's going to cancel. This 9 is really a 3 times 3, and one of those 3's will cancel. So I'm going to end up with 2/3, right? When I bring it over. G sine theta equals A. And you say, Dave, that's not what you got before, which means I screwed up somewhere. I made a mistake somewhere. Where did I make the mistake? It's close. I got 2/5 G sine theta is what I got before, and here I got 2/3. So I made some kind of an error somewhere. My guess is I did the math real fast in my head here. Did I mess this up? 3 halves plus 3. 3 halves is 1.5 plus 3, 4.5. Yeah, that would be 9 halves. Oh, I'm such a dummy. Okay, sorry. The I around the center of mass was not this. The I around the center of mass, that's what we derived before. I know. I'm sure you were yelling at me for the last 5 minutes. Yeah, it's 9 halves mr squared, right? We derived this before, right? Sorry, it's 9 halves mr squared is my I around the center of mass. Okay, now I'm shifting it by a distance r, so I got to add a 3 mr squared, right? There we go, because the mass is 3m. Okay, md squared, right? Okay, so 9 halves plus 3, there we go. So that's 4.5 plus 3 is, sorry, 9 halves, 3 is 6 halves. 9 halves and 6 halves is 15 halves. So this is a 15 halves here, right? And then when I flip it over there, the 3 is going to cancel. I'm going to get 2/5. There we go. 2/5 G sine theta. You say, hey, that's the same thing that we got by the other technique, right? And I feel good about that now. Okay, hot diggity. Okay, hey, let's go ahead and say, I want to show you a third technique now. So that was 2 techniques. Let's do the third technique. Am I going to squeeze on the same piece of paper? Sure, why not? The third way of finding this now, technique 3, is I'm going to do an energy calculation. All right. Now we're trying to find the acceleration of it just in general as it rolls down the hill. And like I was saying, the fact that they're just asking for the linear acceleration as it rolls along and not saying at a particular point means that that acceleration is going to be constant. And if the acceleration is constant, then I can use kinematics. In this case, I'm going to go ahead and say I can use kinematics. And so, right. So I'm going to use I can use rotational kinematics. Now you say, if I think about rotational kinematics, I'm going to say alpha, because I'm thinking about it spinning as it goes. I can use alpha, omega naught, omega, delta theta, and t. Right? And if I'm thinking about translational, I can be doing a, v naught, v, delta xt, right? And I'm thinking about this thing as it goes down that ramp from a start to a finish. Perhaps maybe something like, I'm running out of space here. Sure. It was a terrible picture I'm drawing, sorry. I'm thinking about it starting somewhere and ending somewhere. Let's just draw it from here to here, okay? Starting somewhere, ending somewhere. So here's like the height change. But if I want to find delta x, right, that's really going to be a length along the hypotenuse here, right? And so you say, well, I know that, okay, I'm getting way ahead of myself here. So the point is, I really want to find an a. So I need to have some of this stuff. If I start from rest, then v naught be 0, and that'll drop. That's nice, right? And the final v, and this, and this, and this. What I'm going to do is I'm going to do a combination of kinematics, rotational, translational, with energy, right? I knew I should have gone to a separate sheet of paper. We'll come back to this. So that's going to be the way I'm going to do it. So I'm going to find that final speed using energy, and then that's going to give me enough variables that I can work with here. Because like, here's what I'm thinking. I'm thinking I'm going to use energy to find this, right? Right? And v naught is going to be 0, right? That distance it goes along the ramp, I can just use trig here, right? Call that delta x. That's that distance along the ramp. And you say, oh, well, I can see then that using trig, I say, hey, h is delta x sine theta, right? Okay, or better yet, delta x is h over sine theta. So that'll go in here. And now I've got, I'm going to get this from energy. I'm going to have 1, 2, 3, fourth variable will be that a I need to find, right? And I know that height is going to show up in an energy equation. So I might be able to do some kind of combining them that way. And that's how I'm going to do this. Okay, that's my plan. That's my plan. So going from here to here, let's do an energy calculation. And again, as it goes, we kind of did an energy calculation at the start of this with just the simple cylinder rolling down. So you already kind of know how this goes. As it goes from here to here, what forces are acting? Gravity, normal, friction. And you say, as it goes along, is the friction force going to do work? And we said no, because it's static. It's just each part rolls in and out of contact. It's not sliding. Normal force doesn't do work because it's perpendicular to the motion. Will gravity do work? Yeah. But let's expand the system to include the Earth. So here, I'm just going to whip through this real quick. So here's our energy calculation from the top to the bottom of the ramp. You say, I'm going to have my sigma W is delta K. I'm going to think of it as rotating and translating and changing height, right? My system is the toy and the Earth. Okay, I have no work terms because we talked about friction being static and it not sliding, normal force being perpendicular to motion, and then gravity we expanded the system, so now it's not an outside force. So I'm going to bam. We know that the initial kinetics are 0 because I'm starting from rest. So I'm just going to have k rotational final plus k translational final, and then UG final is going to be 0, so I'll have a minus UG initial. Okay, here we go. So that's going to be a 1/2 I omega squared plus a 1/2 m, but remember the mass is really 3m for this toy, v final squared minus an mgh, but remember the mass is 3m gh. Okay, so that's what that looks like. Yeah. Okay, so from this, I'm going to get an equation for, and you can do it either way, the v or the h. What do you want to get an equation for, v or h? H would be easier. Let's move that mgh over. Yeah, so I'm going to have 3mgh. Yeah, move that over. And now where it says I, I'm going to put in the I for this thing, rotating around its middle, which is 9/2 mr squared. And then I got omega squared. You say where it says omega squared, actually, I'm going to come back, we'll come back to that. And then I've got what, a 1/2 3mv squared. Okay, where it says omega, I'm going to go ahead and use that no slip condition once again and say v is our omega. So omega is v over r. So omega squared would be v squared over r squared. Heck with it. I'm going to do it right now. It's going to be a v squared over r squared. Sorry. And then this r squared and that r squared will cancel. So now I have 9/4. Actually, let's cancel an m out of every term. Bam, bam, bam. There we go. So now I have 9/4 v squared. Here, I'll just plus 3/2 v squared equals 3gh. You're saying that's looking hopeful. So that's 6/4 and 9/4 is 15/4 v squared is 3gh. And so which one do you want to get? H by itself or v by itself? It doesn't matter either way. Sure, let's get the h by itself. So h is going to be, sure, 15 divided by 3 is just going to be 5, right? Five-fourths v squared over g. Sure, why not? Okay, now I'm going to use this with my kinematics. So with kinematics, I came up with an equation here. So look, I've got v naught being 0. I said I was going to arrange for v. All right, fine, I'll arrange for v. It's no big deal. Arrange for v, what's it going to be? Rearrange that, would be 12/15, right? 12/15 gh, the root of that. That's my v. Okay, good enough. If I go ahead and take, now, like I said, kinematics, so now I've got that v, I got these variables. I want the formula that has these. That's going to be the one that doesn't have t. So I'm going to use the formula. V squared is v naught squared plus 2a displacement to get my a. So how about a is v squared minus v naught squared over 2 delta x. Yeah. And so my a is going to be v naught was 0. V squared, that's this guy before I put the radical on. So it'll be 12/15 gh over 2, and then delta x, we figured out from trig here that the delta x is going to be h over sine theta. Okay, so here we go. You'll agree that h and that h go away. When I'm dividing by a fraction, I can multiply by the reciprocal. So that's going to bring the sine theta up top and a 2 on the bottom. And so when I do that, and I bring the sine theta up top and 2 on the bottom, this is going to be 12/15 times 2 times g sine theta. You know, like, hey, 12/15, let's see here. So this is 3 times 5 times 2 over 2 times 3 times 2, right? And so a 2 and a 3 are going to cancel out, and I'm going to end up with 2/5 g sine theta, which is the same answer we got the other 2 ways. So we have now solved this thing 3 different ways and gotten 2/5 g sine theta, 2/5 g sine theta, 2/5 g sine theta, all 3 ways. All right. Which way do you like best? Well, it's up to you. The way they recommended, what was the way they recommended? Oh, that was this. They recommended doing a sigma f as ma and a sum of the torques is I alpha. And like I said, that is the first technique I showed you in class for finding acceleration down a ramp. And then I showed you the pivoting on edge, and that's the other way I showed you in class to do it. It's made more complicated because instead of just pivoting just a simple disk, 1/2 mr squared, you had to remember that the thing is 3 of them stuck together, so the mass is tripled. In your moment of inertia, because there were different sizes, you got this weird 9/2 mr squared for moment of inertia. You got to remember to put in for I. If you're pivoting on edge, you got to remember to do the parallel axis theorem with that. But the point is, it's not too dissimilar from what we've done in class. Doing an energy technique, I think, makes a lot of sense to do also. Energy is just so useful. And because we knew that it was a constant acceleration, we could get away with using this rotational kinematics, or just kinematics actually here, to solve with that energy. All right, so that's that part. Okay, and that was, I want to say, the hardest part of this problem. Was it? I don't know. Let's find. Now it says they want to know the force of friction exerted on the toy as it rolls down the track. So now we need to find that friction force. And you say, well, if I did this energy technique, friction didn't come into any of my calculations before, so I'd kind of be going from scratch if I had done that technique here. That's worth noting. If I do their technique, if I do their technique, then I have equations with friction in it already. And since I found A, I could take that value for A and just plug it back into one of these and solve for F. Look, this one's already nicely solved. So really, because I have a nice equation for friction here, right, which doesn't show up in the other two techniques, that's probably why they chose this one for their example. I'm just going to use this equation real quick and say, oh, friction is 9/5 ma, but the A we just calculated to be 2/5 g sine theta. And so you're like, okay, that's not bad at all. The 2's are going to cancel out. Well, bam, well, bam. And so I'm going to have 9/5 mg sine theta from my friction force. And that's actually like pretty dang fast to do because we already had an equation for friction all solved out, ready to go. So that was that. Again, if I had done one of the other techniques, I chose I chose pivoting on edge specifically because friction pops out of it, so I didn't have to worry about it. But now they want me to go back and solve it. I'd have to go back one of these other ways. In that energy technique, friction didn't matter because it didn't do any work. So we got around that friction thing. Again, I like using those other techniques until they make me solve for friction. I'd have to just go back, and I'd probably do either one of these would be fine once I have A to use. Either sigma F is ma or the sum of the torques is I alpha. Okay, so that's that part. Okay, what comes next? Last part of the problem. Last part. It says, okay, the toy reaches the bottom of the incline and it rolls at a constant speed v along a horizontal section of the track. Derive an expression for the total kinetic energy of the toy while it's rolling on that level part. Express your answer in terms of m, r, v, and physical constants. And so you would say, well, they want specifically to find the kinetic energy. It's clearly going to be an energy calculation. And so you're just going to say, well, energy calculations. They just want to know, in fact, they don't even want to know, they just want to know the kinetic energy. You're going to say, oh, well, the kinetic energy, that's going to be my total kinetic. That's going to be equal to my k rotational and my k translational as it rolls along. And my k rotational is going to be 1/2 I omega squared. And my k translational is going to be 1/2, and I'd say mv squared, but remember the mass is 3 big M is my mass. V squared. And I say, hey, we're allowed to have V, we're allowed to have M. It's just, I'm just not allowed to have omega or I this time. Okay, but I am allowed to have R. So where it says I, I'm just going to plug in our equation for the moment of inertia for this toy, which you remember is that 9 halves mr squared? Yeah, we derived that to be 9 halves mr squared before. And where it says omega, again, because of the no slip condition, again, I'm assuming it's still no slip. I'm going to go ahead and say V is R omega, which means omega is V over R. So omega squared is V squared over R squared. And then I have this, what? I'm just going to combine those. 3 halves mv squared. Okay, hey, the R squared on the bottom, the R squared on the top are going to cancel here. Bam, bam. So now I have 9/4 mv squared plus 3 halves mv squared. So 3 halves is 6/4, 9/4 and 6/4 is 15/4 mv squared. Okay, for my total kinetic at the bottom of that ramp. And that's it. Okay, and that's this problem solved. So like I said, I think to me the most interesting part is that part D here, where they wanted D2, where they wanted to derive the expression for the acceleration, the linear acceleration as it goes down the track. The fact that there's a bunch of different ways of thinking about it, and any of them would have been fine. The fact they want you to solve for the force of friction later makes you want to do a derivation that gives you an equation with friction. Not a big deal to come up with one after that. Either sigma f is ma or some of the torques is I alpha. If you didn't do it that way the first time. All right, that's that problem.